This is the first statistical modeling video for the week of January 28th, 2019, the week of the polar vortex. In this video, we'll talk about how to obtain estimates for regression coefficients using the matrix form of a general linear model. To review, we could write any multiple regression model in matrix form where y is an n by 1 vector of response variables, x is an n by p vector, where the rows represent the observations and the columns represent variables, and beta is a p-dimensional parameter vector. Epsilon is an n-dimensional random error term. I'll jump ahead to slide 25, where we have the matrix form of our normal equations and the derivation of our beta hat, the vector of estimates for our regression coefficients. We can obtain beta hat using a least squares procedure, just like we saw in simple linear regression, by minimizing the sum of the squared residuals. If we let E represent the vector of residuals, this is equivalent to minimizing E transpose E. We talked briefly about this derivation in our last class meeting, and you can find more information on this calculation in the book Applied Regression Analysis by Kuttner et al. The important point is that in the end we arrive at our regression estimate beta hat equals x transpose x inverse x transpose y. Some facts that we use in this derivation include the fact that x transpose x is a symmetric matrix and has the same rank as x, and also the fact that beta transpose x transpose y is equal to y transpose x beta, noting that both of these are scalar quantities when you multiply them out. Let's take a look at our example. We've talked about the problem with predicting SAT scores in a state based on teacher salary and the fraction or percentage of students who take the SAT in that state. In this case, we're fitting a model with an intercept and two predictor variables. We would set up our model matrix X by first including a column of all ones for the intercept term, then a column with the teacher's salaries, and a column with the fraction of students taking the test. The column of y values represents the SAT scores, the average SAT scores in that state. So I can combine these into an X matrix, as you see here. And I've shown the first 6 rows of that matrix corresponding to the first 6 states in our data set. So in our first state, the average teacher salary was $31,000 a year. Note that this is back in the early 1990s, and 8% of the students in that state had taken the SAT. We calculate x transpose x in R, as we see, and we can go ahead and calculate beta hat, the least squared estimates for our coefficients. We find the inverse of x transpose x using the solve command in R and multiply that times x transpose y to obtain our least squared regression estimates: beta 0 hat, beta 1 hat, and beta 2 hat. Note that these exactly match the coefficients that you would get using the LM command in R. Moving forward, you should be able to now compute this first column of the table of coefficients using matrices without having to resort to the LM command in R. If we want to predict average SAT score in a state using information about its teacher salary and percentage of students taking the test, we can do it using our model just as we've done before. In this case, our prediction y hat will be equal to x times beta hat. And since beta hat is the quantity x transpose x inverse x transpose y, all I do is multiply that times x out in front. This matrix we see x times x transpose x inverse x transpose is an n by n matrix, sometimes called a hat matrix or a projection matrix. Using linear algebra terminology, this matrix projects the vector y onto the space spanned by the columns of x. In essence, this is finding the p-dimensional surface, the p-dimensional plane that is closest to the points in our data set. To calculate the fitted or predicted values for the states in our data set, we simply multiply x times that vector beta hat, or x times x transpose x inverse x transpose y, and you can see the results below. These are the predicted average SAT scores for the first 6 states in our data set, and note that they match the output we would get if we used the predict command in R. We also are interested in estimating the error variance sigma squared. We've seen the formula for this in simple linear regression. We just take the sum of the squared residuals and in that case divide by n minus 2. In general, we'll divide by n minus p, where p is the number of estimated coefficients in our beta vector. That typically includes an intercept term along with all of our x variables. We've seen that this quantity in the numerator, the sum of the squared residuals, can be expressed as E transpose E, where E is the vector of residuals. Note that more generally, for a p-dimensional matrix X with rank P, or with any rank, we can write the estimate sigma hat squared as E transpose E divided by n minus the rank of X. The quantity n minus rank of X is known as the degrees of freedom. In our teacher salary data set, we calculate sigma hat squared using the formula that we just saw and take the square root to find the estimate of the standard deviation, which comes out to be about 33.69. And notice this matches what we see in the residual standard error in our output. We have 47 degrees of freedom since we had 50 states and p was equal to 3 for the 2 x variables plus the intercept. Let's consider another example. We look at data that were collected through a nutritional study conducted in the late 1980s on 315 patients. It was believed at the time that low concentrations of retinol plasma or beta-carotene might be associated with increased risks of developing certain types of cancer. To study this, researchers collected data on 315 patients who had undergone operations within a recent time period and collected information on a number of health-related factors of those patients. We'll focus in on a few factors of interest, in particular the patient's age, frequency of vitamin use, average number of calories consumed in a day, average amount of fat consumed in a day, average number of alcoholic drinks consumed in a week, and their retinol plasma concentration and beta-carotene plasma concentration. I've put together a data set with just those variables, and you can see the first 6 rows. Now, to get a better sense of what our data look like, let's visualize them using what we call a scatter plot matrix. In a scatter plot matrix, we create a whole bunch of scatter plots that plot the different variables against each other. Along the diagonal, you see an estimate of the distribution of each variable. For instance, for ages, we see that ages are most frequent around 40 and pretty common up to about 60, leveling off towards 80, and then after that, older patients are less frequently represented in our data set. Moving down a row, we see the distribution of ages for 3 different vitamin levels. Notice that for vitamins, there are only values of 1, 2, or 3, which represent how frequently people take vitamins. We should probably view this as a categorical variable rather than a numeric variable, and we'll talk more about that in a minute. In the next row, we plot age against the number of calories that people consume in a day. Interesting to note, we have someone who claims to consume more than 6,000 calories in a day. Moving down a couple more rows, we also note a rather peculiar point where we have someone who claims to consume more than 200 alcoholic drinks in a week. We might be suspicious of some of these data points and consider removing them from our data set. Looking at the column for alcohol, again we see this outlier, this person who claims to drink a very large number of drinks. We can also get a numerical summary of the data using the summary command in R. A few observations that we noticed. We have someone who claims to eat a lot of calories and also someone who claims to consume a lot of alcoholic drinks in a week. Also, the vitamin use variable, reading in the description, is coded as 1 representing regular vitamin use, 2 representing occasional vitamin use, and 3 representing never using vitamins. We should recode this variable as categorical rather than numeric so that it's handled properly in our model. To do that, we'll do a little bit of cleaning the data. We're going to remove the person who claims to eat more than 6,000 calories in a day and consume more than 200 drinks in a week. Perhaps this person was not being honest in the study, or at the very least does not seem to be representative of the vast majority of people who were interested in drawing conclusions about. We'll also convert the vitamin variable to a factor variable or a categorical variable in R. Now when we visualize the data again, first we notice that the outlier is gone in terms of alcoholic drinks and calories consumed, and also notice that now the vitamin variable shows up differently as a factor variable rather than as a numeric variable. It turns out that the person who claimed to drink more than 200 drinks and consume more than 6,000 calories a day was the same person. So we've only reduced the size of our data set by 1, and we now have 314 observations. We'll summarize the clean data as we see. And now that our data are in better shape to work with, let's go ahead and think about modeling. To start off, let's just consider trying to predict someone's retinol plasma concentration using age, number of calories consumed per day, and number of alcoholic drinks consumed per week. we have an intercept term plus 3 explanatory variables and a random error term. But we want to think about how would we incorporate vitamin use. Remember, vitamin use is a categorical variable for either never, occasional, or frequent use of vitamins. Why might it be a bad idea to use a model where we simply add another term, beta 4 times x sub I 4? Well, for one thing, this is expressing vitamin use as if it had a linear relationship with retinol concentration. It really doesn't make sense to talk about a linear relationship with a categorical variable. Even if I let 1 represent never, 2 occasional, and 3 regular, this would be saying that there's some kind of constant slope, or I could interpret beta 4 as the rate of change in retinol plasma concentration for a 1 unit increase in vitamin use. There's no reason to believe that the change between never and occasional vitamin use corresponds to a 1 unit increase in the same way that occasional and regular vitamin use would. So we shouldn't think about this categorical variable in terms of having some kind of slope related to it. Instead, we should treat each of these as different categories and try to estimate what's the effect of never taking vitamins versus occasionally taking vitamins or regularly taking vitamins. One possible way to do that would be to create 3 variables out of this variable. We call these indicator random variables, or sometimes dummy variables, that either take on the value 0 or 1, depending on whether or not the patient falls into a particular category. We'll let x sub I 4 be 1 if the person takes vitamins regularly and 0 otherwise. Same thing for x sub I 5 for occasional vitamin use, and x sub I 6 for never taking vitamins. So notice that each person will have exactly 1 1 and 2 zeros using this approach. We could then try to write our model using 6 variables where beta 4 times x sub I 4, beta 5 times x sub I 5, and beta 6 times x sub I 6 all pertain to vitamin use. And if we express our model in matrix form, you see what the first 6 rows of the model matrix look like. Our first column represents the intercept terms, so we have all 1s. In our second column, we have the ages of the patients. The third column gives calories consumed per day. Column 4 is number of alcoholic drinks consumed per week. And then the next 3 columns represent either regular, occasional, or never taking vitamins. So we can try to compute our vector of coefficients, our estimates of beta 0 through beta 6, using x transpose x inverse x transpose y. But if we try to do that in R, it spits back an error message. Why didn't this work? It says that x transpose x is computationally singular. That means it doesn't have an inverse. Remember that the rank of x transpose x is always the same as the rank of x, so this means that x doesn't have an inverse either, or x isn't full rank. Looking back at the matrix X, notice that we can always write this first column of all 1s as a linear combination of the last 3 columns. In fact, if we add together the last 3 columns, we'll always get exactly 1 1. And so column 1 can be written as a sum of columns 5, 6, and 7. Thus, columns 1, 5, 6, and 7 are linearly dependent, and the rank of the matrix X is only 6 instead of 7. Therefore, X is not full rank, and we can't find its inverse. So how do we deal with this? Well, in fact, we didn't need to set up all 3 of these last columns. If I knew 2 of them, then I could automatically determine the 3rd one. If I knew whether a person regularly took vitamins or occasionally took vitamins, then I would know whether or not they were in the never category. So we can drop one of these columns. In our situation, we'll drop the column for people who take vitamins regularly. Essentially, what that will do is that will absorb that information into the intercept term, or the intercept coefficient beta 0. So now we'll just set up 2 indicator random variables. X sub I4 will be 1 if the person takes vitamins occasionally, 0 otherwise, and X sub I5 will be 1 if the person never takes vitamins, and 0 otherwise. So we now write our model with 5 variables and fit it in R as you see. And now if I calculate beta hat, it works. I get a vector of 6 coefficient estimates, my intercept term, and then beta 1 through beta 5. Notice that these numbers match exactly what I would see in my R output if I were to use the LM command for our coefficient estimates. An intercept of about 475, an age coefficient of about 2.97, a calories coefficient of about 0.019, and again I'll go back to the ones we calculated using our matrices, and you can see that these all match up. Let's think carefully about how we'll interpret these, especially the categorical variables. For the intercept, our interpretation will be the expected plasma retinol concentration for a person age 0 who consumes 0 calories per day, 0 drinks per week, and uses vitamins regularly. Notice that that regular vitamin use became part of the intercept when we dropped the original X5 column from the model. Of course, this isn't a sensible interpretation by itself, but it's a reference point. We can interpret beta 1 through beta 3 in the usual sense that we've been doing, the expected increase in plasma retinol concentration for each additional year in age when calories, drinks, and vitamin use are held constant. That's for beta 1, our coefficient corresponding to age. The coefficients for the other numerical variables, calorie consumption and alcoholic drinks, have a similar interpretation. But let's think about the categorical variable. We would now interpret beta 4 as the expected difference in plasma concentration, retinol plasma concentration, for people who occasionally take vitamins compared to people who take vitamins regularly when the other numeric variables, age, calories, and drinks, are held constant. Similarly, for beta 5, we would interpret that as the expected difference in plasma retinol concentration for people who never take vitamins compared to people who take vitamins regularly when the other variables are held constant. To emphasize, we're interpreting the coefficients for our categorical variables as the difference between people who take vitamins from that category, either occasional use for beta 4 or never for beta 5, compared to the baseline category that was part of the intercept, in this case regular vitamin use. So to interpret those coefficients in our model, we would say a 1-year increase in age is associated with an estimated average increase of about 2.97 nanograms per milliliter of plasma retinol concentration, assuming that the other variables, alcoholic drinks, calorie consumption, and vitamin use are held constant. Calories and alcohol would have a similar interpretation. And then for the categorical variables, we would say that on average, a person who takes vitamins occasionally is estimated to have a plasma retinol concentration 6.7 nanograms per milliliter lower than a person who takes vitamins regularly, assuming age and calorie consumption and drinking habits are held constant. Similarly, on average, a person who never takes vitamins is estimated to have a plasma retinol concentration 32.2 nanograms per milliliter lower than a person who takes vitamins regularly, assuming that the other variables are held constant. If we go back to the LM output in R, notice that only the coefficients on alcohol use and age are statistically significant. So we only have evidence of a relationship between age and retinol plasma concentration and alcohol and retinol plasma concentration after we account for the other variables present. If we want to estimate the error variance, we'll first calculate y hat, our predicted values, by taking the projection matrix x times x transpose x inverse x transpose y and creating our vector of predicted values y hat. We found the rank of the matrix and n, the number of rows in the matrix, or the number of observations. So we can calculate an estimate of the error variance by taking the sum of the squared differences between y and y hat, and then dividing that by n minus, I called r, the rank of the matrix. Notice in this case that would be 6 rather than 7. And I calculate sigma hat squared and take the square root to get my estimate sigma hat, which again, notice matches what you see in the residual standard error place in the LM output. So at this point, we're now able to calculate the entire first column in our coefficient table, as well as the residual standard error. Soon we'll talk about how to calculate the second column, and after that we'll be able to produce this entire table without relying on the LM command in R. We'll end our first video there.